We're going to start. So we're going to start with a geometry problem, which you guys can help me figure out.
Geometry's in high school.
Okay. You guys remember how to find the area of a parallelogram?
Based on height.
Oh, based on height.
That's how you find the area of a parallelogram.
Professor, isn't it based on height?
Can you just break it into smaller
Okay.
parts?
So,
A cross product.
so you take, yeah, like back in high school geometry, little like 9-year-old kids, just do a cross product. Okay, let this be a matrix and consider that we take those as vectors, just an interesting experiment. So I'm going to take one vector to be AB, another vector to be CD, and I plot those in the xy plane. Let's say AB is here. This is the vector AB, which is V1, and this here is V2. Okay, so, and again, we can create like a parallelogram from these, sort of like that's how you find the resultant vector, right? That's if you add these two guys. So let's say I did, this is supposed to be, anyway. So let's say I did that and I want to find the area of this parallelogram subtended by these two vectors. That's going to be the goal. Right, so I imagine I can use these vectors to create a parallelogram. Now, if that's this, what is the value here? This is V1. This is A comma B. Okay. That has distance A, right? And so the Y value over here would be
B.
that would be B. Okay. And what about this one here? Right? Look at the X and Y components of that one.
C.
Here, C. Here, D.
D.
So let's say I bring this over here. So what would be the X component of this?
A plus C.
A plus C.
A plus C.
Okay. And what will be the Y component of this?
B plus C.
B plus C.
D.
Because that's according to the resultant vector. So your intuition from vectors in R3 can help you here. Vectors in Calc 3 can help you. Okay. So now, let's say I want to find the area of this parallelogram. And you might not remember that the form for the area of a parallelogram, and in either case, it would sort of be hard to apply it here because you have to know about the perpendicular height is involved in the area. So you have to figure out the length from this corner to that, and that's kind of going to be annoying. So what we can do is find the area using subtraction. Notice here, I have a rectangle. And so what I'm going to do is I'm going to take the area of the rectangle, subtract the areas of all these pieces, and then use that to figure out the area of the parallelogram. So that's going to be the strategy. So let's actually see what that is going to be. So area of the parallelogram equals area of big rectangle minus area of unshaded pieces. That's going to be my strategy. Okay. Let's actually put that into practice. What can we figure out from that? What's the area of the big rectangle?
A plus C.
A plus C times B plus D minus, now let's subtract all these small parts. What I'm going to do is dissect these into some nice shapes. Here, this is a right triangle. I can cut this here into another rectangle. And this here will be another right triangle. I can cut this into a rectangle. And that would be another right triangle. And this would be a big rectangle. And hopefully you remember how to find the areas of all those things. So let's actually do that. Let's start with this guy. What is this?
B plus D minus D.
Right? So it would just be
B.
B. And the width?
C.
So we're going to subtract BC. Okay, what about this one?
Half A times B.
This, the rectangle is right.
Oh, right.
So that would be B
C times
times
B times
C.
C.
okay. All right, let's do this right triangle here.
Half
1 half A times B.
Half
One
base
half.
times height. So that's going to be plus 1/2
AB.
AB. And that's that guy gone. What about this one here?
So
This right triangle here.
so that would be
Half C times
half C times and
B
then
minus B.
Plus half C times.
B minus B.
D.
2B plus D.
That would be D, right? Because the height of this is B and that's B plus D, so this is D. And that's, get rid of that. This one,
Which one?
this right triangle.
So that would
Half
be
B
1
plus C.
half B plus D times C.
Half D times C.
What? That's, the height is D,
D. Oh yes.
and what is the width?
C.
So that would be C.
So that's what, 1/2 CD again?
Mhm.
What about this one?
1 half A times B.
Plus 1/2 A times B. And that was that. Okay, so hopefully we did that correctly. Let's actually simplify this. So this becomes what? AB plus AD plus BC plus CD minus BC minus BC. These guys add up together, right? So that's minus AB minus CD. And what does that simplify as? So AB kills the AB. I have AD. And then I have the CD kills the CD. And then I have B plus BC minus 2BC. So that gives us minus BC. Okay. So this guy here is the area of the parallelogram. One thing I want you to note, it's more accurately. Its magnitude, AB minus BC, is the area of the parallelogram. Because you'd realize that if you actually swap the orientation of the vectors, or you sort of rotate it into one of these things where the x or the y coordinates are negative, you could possibly get the negative of this guy. But it remains, the fact remains that this expression becomes an important thing when we're looking at two-dimensional vectors. It's an important quantity in the sense that if you create the parallelogram using the resultant vector, this expression, its magnitude, gives you the area of such a parallelogram.
Professor,
Yes?
isn't it the general formula for the area of the parallelogram is base times height? Is that true? Or
Huh?
from
Yes, base times perpendicular height. But the perpendicular height would be difficult to figure out in this case.
Okay.
or at least a lot more challenging than doing this. Yes, Jonathan?
Doesn't the cross product give us an orthogonal vector though? To the other two vectors? So like, how is
Yes,
it also
in
the
3
area?
space. We're in 2 space here, so it doesn't really apply.
So is there like some correlation between orthogonal vectors and the area? Between them? Hopefully not.
Yes, there is. And you actually looked at that in Calc 3, but I'm not there yet. We're still in 2Ds for now. We're still in 2D. We'll talk about 3D in a little bit. Now consider this. Look at this system. Let's call this E and F. So let's pretend something, assuming a unique solution exists. We'll generalize the other cases soon. But when a unique solution exists, it will actually be obvious from us trying to actually solve this. I'm not going to use row reduction, even though we could. I want to use something else. We're going to do, say, elimination. It's just a 2x2. Let's not bother with the row reduction. So one way I can do it, let's say I want to solve for B. Okay, so let's eliminate the x. What can I do here?
AC, common.
Yeah, but then I would get d over c. I don't want to actually get fractions here. Let's keep it simple.
Wait, what do you want to do? Like,
All right, fine. I'm going to eliminate the y.
so that would
Okay, so I'm going to multiply the first one by d. Okay, so this is equation 1 times d. And let me multiply this one by minus b. So that's equation 2 times b minus b. Now if I add them, what do I get? I get AD minus BC x equals, because this guy would die, DE minus BF. In other words, my x would be DE minus BF divided by AD minus BC. Now there are two things that should be interesting to you here. One is this obviously tells me when the x would have a solution, right? Because if I divide that by, if this guy that I just divided by is 0, that's a problem, right? But as long as that's non-zero, this is always what the form of the solution is going to be, right? So that actually tells me about when a solution might exist. Second thing you might have noticed is that look at the denominator. It happens to be the area of the parallelogram when I look at the vectors A, B, C, D. Let's continue. And by the way, it's also worth mentioning that the top is kind of the area of the parallelogram if I did two other vectors. In fact, that would come from the vectors if I did, if I looked at V1, V2. If I took V1 to be EB and FD, that would be the area formula for the parallelogram. Let's solve for the y. So I'm going to go back here, I'm going to do a similar process. Now I want to eliminate the y. Now I want to eliminate the x so that I can solve for the y. Right? So what I'm going to do is, since there's a c here, I'm going to multiply that by a c. So last time I eliminated the y, so now I want to eliminate the x. So I'm going to want to make these a common term. So let's multiply this by minus c. And let's multiply this one by a. let's add those two again. So here I multiply equation 1 by minus c. Here multiply equation 2 by a. Now I can add these two and those would cancel. Here I would get AD minus BC times y is equal to AF minus EC. And so this would mean my y is going to be AF minus EC over AD minus BC. And there's that guy again. So I look at the 2 by 2 system in terms of the vectors A, B, and C, D. Turns out solving for the variables, assuming there's a unique solution, the guy that gave me the error of the parallelogram somehow shows up in the denominator. I'm starting to think that this expression AD minus BC is an important expression. So you know what? I'm going to give it a name.
Rockin'.
It's useful geometrically, it's useful when I'm solving systems, so it's also useful algebraically. Let's name it. So given A equals a matrix A, B, C, D, we call AD minus BC its determinant. In other words, more specifically, I just found what we call the determinant of a 2 by 2 matrix. AD minus BC is the determinant the 2 by 2 matrix A equals A, B, C, D. Now let's talk about notation. There are two ways I can denote this. One, it sort of gives me a real number, right? Because if these are real numbers, that's going to be a real number. So it seems to be some sort of magnitude. It's not a vector. It's really a scalar quantity. So we use the magnitude notation to describe it. I will describe it this way. I would use straight bars, right? So now you need to, that's actually going to be important. So when you're writing matrices, you can use large parentheses or you can use the brackets. But when you use straight line bars, you're referring to this thing we call the determinant. Or you might write det of A to mean the determinant of A. Let's go up one dimension. We can do this analogously for three vectors that are each three-dimensional space. So say I wanted to do something like this: A, B, C, D, E, F, G, H, I. This would be the determinant of the 3 by 3 matrix. A, B, C, D, E, F. That should look familiar.
That's IJK, Professor.
It's kind of like the same thing with the IJK. Remember we were doing finding curl? IJK was in this position, but you actually saw this specifically, this kind of application in Calc 3. This was what we call the scalar triple product. And it actually was a generalization of what happened in 2D. It didn't give us area, it actually gave us a volume. It was the volume of what we call the parallelepiped, which is just basically a parallelogram that's more than 2 dimensions. Parallelepiped. created by 3 vectors, by A, B, C, D, E, F, and the G, H, I. The vector, not the insurance company. So basically in 3 space, so the x-axis, y-axis, z-axis, you have three-dimensional vectors. Basically what you do is you create a parallelogram from each pair of them. And you sort of created this I'm totally messing this up. It's hard to draw from an angle. So I could have one vector here, one vector here, one vector here, and if you create the planes with every 2 pairs of vectors and with the resultant vector, you get what we call a parallelepiped, which is like a 3-dimensional parallelogram, and it turns out that this expression would give you the volume as computed in Calc 3. And so that's called the determinant. And so we can now make a general definition about what a determinant is. And I'll come back to the algebraic definition soon. The one where it shows up in the solution to a system of equations. The generalization of that is what we call Cramer's rule. But right now I'm going to give you a definition in terms of the geometrical definition. So let A be an n by n matrix. Then definition. The determinant of A is a real number whose magnitude gives the volume, or hypervolume if it's more than 3 dimensions, of the n-dimensional parallelepiped. Here's our goal. Let's figure out how to do this in general. So you tell me an n, so it could be a 2 by 2, a 3 by 3, a 7 by 7. I want to figure out some sort of generalization for the volume formula of the n-dimensional parallelepiped formed by this figure. Now, there are many definitions for this. We're going to look at one. And the process is basically what we did with the 2 by 2 case. They sort of figured out, okay, let's look at the hyper cube and then slice away pieces that what we end up with is this parallelepiped. And so you can do, they did that in, basically in 3 space, they created a cube around this and then they figured out, okay, this is, painstakingly they figured out the formula that would give that, and it turns out it was exactly the formula that gave you the curve. Or the cross product of 2 vectors. And so they can do that in general. And so that formula, when they defined the cross product, and it was a bunch of stuff, subtracting a bunch of stuff, it turns out that it was really that process. They really took their intuition from the geometrical picture. And they realized that being able to find this volume is a useful thing to do, right? And so we want to develop a general process for doing this. We're going to look at one process called Laplacian expansion. Named after the mathematician Laplace. It's also known as cofactor expansion.
Professor,
Yes.
wait, is it the same thing with the Laplace transformation in?
No, completely different. It's just Laplace is a mathematician. He would have done several things. So like Euler, there's a bunch of things named after a bunch of mathematicians. They're not always exactly the same thing. Like a Laplace transform is a completely different thing. So a Laplace transform is something you would learn in differential equations. It's a completely different thing. It's not the same at all. So we'll need some more definitions. So we're going to sort of do this in general because we want to do it in general. So let A1, 1, A1, 2, A1, 3, A1, N, A2, 1, A2, 2, A2, 3, A2, N, A3, 1, A3, 2, A3, A3N, all the way down to A1, A2, A3, ANN. We define the ij minor of A, which we will denote Mij, to be the determinant from removing the ith row in the jth column. So for example, for this matrix, what if I wanted you to find M of 3, 2? So basically what that says is you go in the matrix, you find the third row, the second column. That'll be this guy. And what you're going to do is you're going to eliminate that row and eliminate that column. Similar to what you do with ij, but we're generalizing it that you can do it in any position. And then the matrix that's left over, you find the determinant of that matrix. So I'm going to use the straight line bars. And basically here I would have A1, 1, but the next guy would be A1, 3. And that goes down to A1, and A2, 1, A2, A2, 3, and that goes down to A2, N. The next guy in this would be A4, 1, A4, 2, all the way A4, 3, all the way down to A4, N, all the way down to AN1, AN3, all the way down to ANN. So you notice I just removed the third row, second column and third row. There's a matrix that's going to be left over. I define the minor to be the determinant of that matrix. Here's another definition. The ij cofactor of A is minus 1 to the I plus j of Mij. So basically I go through, I can find all these minors, and I'm actually going to change the signs of these guys using this formula. right? So notice that for some powers there's going to be a positive number, while for some powers there's going to be a negative number, right? And this is essentially what we're doing, is we're adding some volumes and subtracting some volumes in a strategic way so that we end up with the volume of the parallel pipe. So, example. In this case, for this matrix, if I look for C32, that is just going to be -1 to the 3 plus 2 of M32, which in this case is just going to be the negative of M32, which is going to be the negative of that matrix that I had here. Now personally I don't like memorizing formulas, so whenever there's a method for not having to memorize it, I usually take that as well. There's a way that you can remember how you would apply the signs. There's always going to be a plus sign in the top left corner. Right? Because that would be the 1/1th position. So that's -1 raised to the 1 plus 1. That's -1 squared, that's going to be a plus. Now when you start moving over, right? So now the power is 1 plus 2, that's odd, that's going to be negative. So there's going to be a minus sign, then a plus sign, then a minus sign. And this will alternate. Same thing here, it will alternate.
What's that first word?
Huh?
The first word?
Mnemonic.
Oh,
It's a fancy word for memory device. Right? And this pattern will repeat. So all you have to do to remember the signs of all the minors is just the minor for a certain position will take the sign according to this chart. Right? Always going to be a plus in the top left, alternate the signs otherwise.
Wait, don't erase it. I'm not done it.
Professor,
1 minute.
Yeah.
Professor, I got a question, cause, alright.
Mhm.
So, I see how you put that in the determinant, but then when you go down to the definition and you got the ij cofactor of A is -1 raised to the I plus j.
Mhm.
Where did that come from? You just saying that that's what it is, or you?
Yeah.
So wait, so you just put that up there and we write it down. What does that mean?
What's that?
That's the principle that I'm trying to. I mentioned the principle. I didn't show you how to derive it, but I'm just saying this is what the
I
answer
don't
would
see the
be.
derivation, but I just don't really know. Like from there, that's where you lost me. Then you got C32.
Remember what we were doing in the very first example, where we had the 2 by 2. I don't know if you copied it.
Yeah, I did.
And so the area was what? Before we simplify it to 80 minus BC, that had a bunch of things, right?
Yeah,
What was
yes.
it?
Which one, X or Y?
For the 2 by 2.
Oh, it was AB minus BC.
No. Before we simplified, the very first step, when I added all the stuff and then I subtracted all the things.
Oh, it was A equals AB plus AD plus BC plus CD.
AD plus AD plus BC.
Where you at? Oh, BC plus CD minus BC minus BC minus AD minus CD.
Right. So it turns out there's a systematic way of doing this. Some of them got a plus sign, and some of them got a minus sign.
Okay.
This is the strategy for how you get those signs.
I understand
essentially
the
is what I'm
mnemonic.
trying
I
to
just
say.
don't understand that one part. Okay, that example, C32 equals -1 raised to the 3 plus 2, and what I don't.
I'm
what is
applying
that?
this formula.
So that's a formula?
Yes, this is the formula for the cofactor.
But why is it 3 plus 2?
Because that's the I and the
M32?
J. The I and J are 3 and 2. I
Okay, so you just put
J.
that up there, and then you put, okay, so then you plug that in?
Yeah,
and then
they're
what?
just plugging in the formula.
And then what? Once you plug that in the formula, then what?
And then that would be minus times the determinant of this.
Okay, and then what? Like, I'm trying to see what this is. We just. We just making a determinant? Like, what are you doing?
We're building up a determinant. That's exactly what I'm doing. I'm telling you how to build the pieces that we're going to put together into a big formula
Are
to
you gonna
compute
do
a
an
determinant.
example? Or you've been doing examples?
I never do examples in this class, ever. Like, I just talk about theory and then I move on.
But Professor, I don't get it. I
Okay?
see the formula and I know what you're doing, but I don't know what you're doing at the same time.
Okay, make sure you learn the important things. This is important. The mnemonic to remember the signs.
Alright,
And how to create this matrix is important.
okay.
Professor, can you do an example
Why you
of
can't
that
do a small
matrix?
one, Professor? I don't know what you're doing. Can you do like a little baby one or something? So I
No,
can
the
just see
big
it?
matrix. The determinant. Can you do an example?
Honestly, I never get when students ask me that question. Can you do an example? Have I ever taught you anything and not give you an example?
No.
Ever?
Yes,
What? What did I do?
all the time. Like when the test comes and you start throwing stuff. Come on, you know what you're doing.
Anyway, we're gonna move on. So now let's do a definition.
A definition and not an example, you see?
Let A be an n by n matrix. The determinant of A is equal to. Now I'm going to give you a formula for the determinant of A.
N by N matrix.
So this is going to be the formula. Do an example. I can just imagine what's going to follow this. Me writing this down. So I can.
I mean, does this formula always work? Because if so, I'm really excited.
Okay. So this is going to be Aij
What is A for?
multiplied by theCij's, where j goes from 1 up to n.
Come on, Professor. You know I don't know what that is.
This is determinant from expanding along the ith row.
A and C for.
We can also use we could also let the i's change.
Does this all only work for square matrices?
Yes. This is from expanding along the jth column. One thing you want to note here, which is going to be different from the crossbars that we've usually been computing in the 3x3 case and higher, is that you can choose any row, or you can choose any column to expand on. The answer will be the same. For example, if A is a 3x3, I can do the determinant of A is AI1 CI1 plus AI2 CI2 plus AI3 CI3, where I represents the row I need. And that's basically going to be the answer, right? So you can say, for example, let's say I want to expand along the second row. The formula for that determinant is going to be A21 C21 plus A22 C22 plus A23 C23, where this is just the position in, these are just the numbers from the row of the matrix. These are the numbers, the determinants that you get by eliminating the second row and the first column. And once you do that and you compute all these, you will get a number that's actually going to be your determinant. Example. Since I've never given examples ever, let's just try it. Let's try it this one time and see how it works out, if it makes a difference. Here's a matrix. Find the determinant of it. So, first step is to choose a row or a column that you want to expand along. So we call it Laplacian expansion. And then we can move. What would you think would be a nice choice?
That top one, bunch of zeros and ones.
Yeah, J2.
Wouldn't it be easy to find the second one because you have more zeros?
Second what?
I1.
No, the second column.
Yeah, J2.
I mean,
Second column
Yeah.
looks pretty nice.
Oh,
Why?
yeah.
because you
In
have
that line,
more zeros.
they're the most zeros.
Oh.
Since I know I have this formula where I'm going to be multiplying a bunch of stuff, I don't want to multiply too many things. So I can choose, since I have the choice of any row or column, I'm going to choose the one with the most zeros, so I have to compute less things. So that's one important choice. So that's the first thing I would do. Choose row or column with the most zeros. That seems to make sense based on what the formula is going to tell me. So let's say I choose that. Now I'm going to have to compute this formula. For one thing, notice that the C's come with signs. How do I remember the signs? Well, I remember that pattern that I did. So the plus one, there's going to be a plus sign in the top left always, which means the sign is going to alternate. This is going to be a minus. This will take a plus sign. This will take a minus sign. This will take a plus sign. And so now let's actually do the expansion. So we're going to go through, and I'm going to put each number in front of the cofactor for that position. So I'm going to write it out now, but you don't have to write it out if there's a zero in general, of course. But I just want to show you that I'm applying this formula. So the first one is minus 0 times the determinant of some matrix. And what is that matrix going to be? Well, block out everyone in that row and that column. And you see the matrix that's left over? That's going to be the guy I'm going to write down. 3, 2, 2, 1, minus 2, 1, 2, 0, 1.
Oh my god.
I was like, I get it.
Plus, move to the next guy. 1 times the determinant of some matrix. Which matrix? Block out everyone in that row and that column and write down the remaining. So it's 1, 0, minus 1, 1, minus 2, 1, 2, 0, 1. minus 0, block out everyone in his row and his column, and we would have 1, 0, minus 1, 3, 2, 2, 2, 0, 1, plus finally 0, which is the last one. Block out everyone in that row and that column, and we'd be left over with 1, 0, minus 1, 3, 2, 2, 1, minus 2, 1. Now obviously, this is all 0, that is all 0, that is all 0. And you don't have to actually write that out in practice, but I just want to show you an example of how you go. If these were not 0 numbers, you'd have to write them down. But clearly you can say if I chose the second column, I can just ignore this and this and this, and I would only write this down. So the first thing you'll realize here is that I went from a situation where there was a 4x4 determinant that I had to deal with, to now there's a 3x3 determinant that I have to deal with. And so you continue the process again. So this method, really what it does is it breaks it down to a case that you fully understand. We fully understand the 2x2 case, that's just the AD minus BC, that little cross product. And so that's what we're going to do now. We're going to continue this and break that down. So this is going to be equal to the plus 1 times, I'm going to redo that process for this matrix. So which row or column you want to choose?
Second column.
Second column is again the best one to do. That's the guy with the most zeros. So this is going to be 0 times blah, I don't care. And it's going to end with 0 times blah, I don't really care. But the middle one, this will be a plus, minus, plus. So the middle is going to be minus 2 times, technically this would be minus 0. Block out everyone in that row and that column. We're going to have 1, 1, 2, minus 1.
Professor,
Yes.
so since we started with the second row, this one, so that has been negative. Okay.
What?
Never mind. Never mind.
Okay. This obviously you can ignore, this you can ignore. So now we end up with 1 times minus 2 times this guy. Now that guy is the 2x2 case. We know a nice form for that. This times this minus that times that. So it's going to be minus 2 times 1 times 1 minus 1 times 2. And that would give us what? Minus 6 ultimately.
But why that 2 would be negative?
Wait. It's negative here.
Oh.
Plus negative.
It's plus times a negative 2.
Okay.
Plus 1 times a negative 2. And so of course, this is basically the process, right? You kind of do this manipulation, and if you start with a large matrix, you break it down to matrices that are one-dimensional lower. Then you keep breaking that down, breaking that down, breaking that down. So the idea is, of course, if I gave you a 5x5, you break that down to a bunch of 4x4s, and break those down to a bunch of 3x3s, and break those down to a bunch of 2x2s. And at the 2x2 level, you have a nice little form. You just do this times that.
And that's what you're gonna do, right? There was a
And
5x5.
that's exactly right. I'm going to give you an 11 by 11.
Okay.
Yeah.
So that has been a tough
And
lump.
so this would be the determinant of this matrix.
And that helped, Professor. I did understand that example, just so you know.
Yeah, I'll probably start giving examples all the time.
Professor,
Yes.
so when we do a cross product, it's kind of like expanding like that first row.
Yeah, and when you did if you were to do a cross product of I, J, K, and you have some matrices A, B, C, D, E, F, the way you've done it is you've always expanded along the first row. And that's kind of why when you got to the J vector, they always say change the middle sign. It's because the determinant form. That's why when you're doing finding the cross product of something, it was, you block out everything in this, remember? You do this times this minus that times that. Then you block out everyone here, this times this, that times that, and then you change the sign for some mysterious reason that they never told you about. And then you came over to the k, you block out this times this, and then that times that minus that times that. What you're doing is finding the 3x3 determinant, but they kind of taught you to always expand along the first row. But you can go back through all your Calc 3 stuff and you can check literally any row or column you picked, and you did that similar process, you would have gotten the same answer all the time. So they told you a cross product, and they just say, follow this rule, that's how you compute a cross product, don't worry about it. The answer is, it was a determinant. There was a meaning behind it, and this was the process that caused it to be.
Well, that's how I like it, just straightforward.
Exactly. Just follow the front, don't think.
You know?
Don't worry about where this came from, this is the answer, just do that. Don't worry about it, just do this. Okay. So that's the determinant. Now, there should, am I going to tell you about that? What should I tell you first? Don't know if I have time to do that. Let's do a corollary. This should be, I'm not going to tell you how this works, but let's say, so if we have an upper or lower triangular matrix, then the determinant of A is just the product of all the diagonal elements. So that means if your A looks like this, right, so here's the main diagonal here, and you have non-zero numbers up here, but you only have zeros below. It turns out you can find the determinant of such a matrix very easily. Just multiply these across. And to see why that's true, basically what you can do is just follow the pattern of expanding along the first row all the time. So if I expand along the first row, I'm just going to expand along the first column. Then all of these guys won't matter. I'm just going to take this times that, and then you expand along the first column, and then that's not going to matter, and that's not going to matter, and it's going to literally break down. You'll get all zeros in the columns until you get down to the last step, or by similar reasoning, if all your non-zero numbers are in a lower triangle down here, but they're all zeros up here, you can, again, find the determinant just by multiplying down along the diagonal. Which would be, again, easier than this. But it's still following the same process, but you can just sort of skip steps in those situations. So now, I guess some of you might be concerned, oh, John's going to give me like a 7x7 to do, and you're going to be worried about it. I know he's not going to put any zeros, because that's how you want it.
Yeah.
So knowing that this way is kind of easy, you might be wondering, is there a way to put zeros into the matrix and compute the determinant if Javon doesn't give me any zeros in the matrix?
Yes.
Oh, you want us to do that?
And the answer is, of course, yes. Right? Now you might worry about, well, if I start messing with the matrix, isn't that going to change the answer? The answer is it might, maybe. But the good news is we actually know exactly when this will happen, and we can predict how it will happen. And so that will lead us to some theorems that I'm going to mention now. And in these theorems, the operations, I want to make sure, this is particular for type 3, it is assuming you're doing the operations exactly as defined in earlier, okay? So normally when you were doing like reducer echelon form and stuff, technically there are times when we're kind of doing two row operations at once and we weren't really following the definition, but you really have to follow the definition for this. So for example, in a type 3, it specifically says you need to replace a row by itself plus a multiple of some other row, right? So the row you're replacing, you're not supposed to multiply by anything, for example. Okay, so you have to be very careful of how you're looking at the rules. But so, that being said, let me just tell you some theorems that we can talk about here. Theorem 1. I'm not going to prove it, I'm just going to tell you these facts. Performing one type 1 operation negates the determinant. You might remember a type 1 is when we switch two rows. So let's say you have a bunch of zeros, but they're not all lined up. You want to get them to line up, and you can do that by switching a bunch of rows. You need to be aware every time you switch a row, it multiplies the determinant by a negative sign. And so that way you can keep track of what the answer would be. Right? So the ultimate goal is I'm going to show you a method of how to create zeros when there are none there to cut down on the calculations that you have to do. Right? So you should be aware when you're doing row operations, they will affect the determinant in a certain way, and a type 1 negates the determinant. Swapping two rows, so if I take a matrix and I find a determinant, if I swap two rows before finding a determinant, I'll actually get the negative of the original answer. And this has something to do with orientation. Just do this and don't worry about where it comes from. That's what I'm saying. Okay, yep. Here's another theorem. 2. Performing a type 2 operation with scalar k not equals 0 multiplies the determinant. By k. So let's say you're changing a row and you decide to change it by multiplying through by some non-zero number. If you find the determinant now, the determinant itself will be multiplied by that number. So let's say, in order to make the determinant easy to compute, I multiplied a row by 2. It means that the answer that I get would actually be 2 times the determinant, so I need to remember to take a half of that answer, and that would be the determinant of the original. Yeah.
That's even if you don't use that row?
Yes, regardless. And it's easy to see if you use the formula that I showed you. If you imagine in front of all the A, I, J's, I put a K, that K would factor out and multiply the entire sum. So in other words, what I'm saying is, basically what this is saying is if we get B by swapping two rows of A, then the determinant of B is going to be the negative of the determinant of A. And this one is basically saying if we get B by multiplying a row of A by K, then the determinant of B is going to be K times the determinant of A. Here's another thing. A type 3 operation does not affect the determinant at all. I.e., if we get B by performing a type 3 operation on A, then turns out the determinant of the new matrix is exactly the same as the determinant of the first matrix. And again, the warning here is follow definition of type 3 exactly as defined. Meaning when you're doing a type 3, I'm considering that you're changing a row by using itself plus a multiple of some other row. The row you're changing should not be multiplied by anything. You need to multiply some other row and add it to that row. That's a type 3 operation, and it turns out doing that does not change your determinant. Now there are some consequences of these, but I want to do another example so you can see how I'm going to use this in action. Find the determinant of this guy. Notice there are no zeros here. So you can brute force it and just do expand along any row or column you want and do 3 2x2 determinants. But I want to illustrate this method, which it will work for any size, but I'm just going to illustrate it with 2x3. And personally, I try to force myself to use a type 3 all the time because that's the only one that doesn't change, as opposed to doing one of the other two and then I have to remember, oh, I have to multiply by a negative sign, then multiply by a negative again, I need to divide by 2. Like if you're using theorem 1 or theorem 2, you have to keep track of the changes you're making because you have to undo those changes at the end. If you're doing a type 3, you don't have to do anything. And so if you keep doing type 3s, you don't have to worry about changing the answer. And so that would be nicer. So I would keep using type 3s if at all possible. So the trick here, the goal of what I would want to do, is that if I'm given some matrix 3x3 or even larger, and there are no zeros, I can use the fact that I can use row operations and I know how they'll affect the determinant to create zeros. So notice here, this would be the same as the determinant. Right, the matrices are not the same, but the determinant is going to be exactly the same. Let's say I did 1 minus 2, 3, 2 minus 1 minus 1, and I'm going to change the third row by taking row 2 plus, well, let's do row 3 plus row 2. I'm putting row 3 in a circle because make sure you do not multiply row 3 by anything. It's always 1 times row 3 plus a multiple of some other. So if I do that, what would I get? I would add these two, I get a minus 1. Adding those two gives me a 0. Adding those two gives me a 3. And it turns out when I'm finding a determinant, that actually will not change the answer. I've just created a 0. Let's actually do it again. That is also equal to, so notice here, this is a type 3 I just did. So let's actually do it again, right? So I just created a 0. Let's see if I can create another 0. Where else would be a nice 0 to create? You want to create a 0 in row 1? We're using row operations, so we need to do rows. Notice here, That's a nice type 3 operation right there, just waiting to happen, right? Like 1 plus a minus 1. So what I can do is, again, I can change row 3 by using itself plus a multiple of another row, which I'm going to take as being 1 times row 1. So when I add these two, oh no, but we don't want to do that, right? So you can see what the problem is going to be. I'm going to kill the 0 here, so no. You have to be careful. You're thinking along the right lines, but you need to be careful
Why
of the
don't we do
consequences.
now this new R3 times, or plus 3 times R2? Where?
R1 plus
Oh, no,
Can you
no,
make that as a 1? Like,
R1 plus,
no, the second row,
negative.
you have a negative 1, make that a 0 somehow.
okay, and how would I do that?
So, it would be negative 2 or no.
What I would do is I would try to make a 0 here
Okay.
to avoid fractions, and that would be nicer. So if I wanted to make that a 0, how would I do it?
You multiply 2 or 2 or a negative.
So 1, I need to leave row 1 alone, because I'm going to change row 1. And I need to add a multiple of some other row.
So 2 or 2 or negative 2 or 2.
Minus 2 R2. So leave this alone, multiply that by negative 2, that's minus 4, and add them. I would get what?
Negative 3.
Minus 3. Leave this alone, multiply that by negative 2, and add them. I would get 0. Leave this alone, multiply that by negative 2. I would get 2, and add them. So notice now, in the second column, I've created 2 zeros that weren't there before, and in terms of the determinant, it's the same answer. So now I can say the determinant of, let me call that matrix A. Now I can just expand along this, which means that you're going to have to remember the sign. There's a plus, minus, a plus, so that becomes a minus 1 times, block out everyone in that row and that column, minus 3, 5, minus 1, 3. So it's this times this, which is minus 9, minus that times that, minus 5. So that becomes what, 4? Enter, that's the answer. Now for a 3 by 3, this is kind of overkill, but for larger things, this is actually a very useful thing to do. And usually, if you're telling a computer to find a determinant, and you give it a very large matrix and there are not many zeros, the computer will more than likely do a bunch of row operations to create a bunch of zeros so that it can find the determinant easier. Computer, because it does arithmetic very well and it does addition is easier than multiplication, what it will do is a bunch of row operations to get it in like an upper triangular, and then just do one multiplication down along the diagonal. But you can create zeros wherever you want. The process of this is, by the way, oh, just one more thing.
Professor, so don't you need to undo the things that you did, like to convert into that?
No, I did type 3s. I don't have to undo anything.
Oh.
There's a name for this. The general process of using row operations to find a determinant, make a determinant easier, it's called pivotal condensation.
Just the extra credit.
What? Extra credit for what?
Definition.
No. That's just the name of if you ever want to refer to it.
Professor?
Yes.
So if you're doing
The idea is you want to concentrate the determinant on one guide, which is called the pivot for the determinant. Yeah.
if you're taking a determinant of bigger matrix bigger matrix, you would have to use other types, which would force you to.
You wouldn't have to use it, but it's an option.
But didn't you mention before that for bigger matrices you would have to back calculate? to see.
Depending on what you're doing. If you use like a type 1 or a type 2, you'd have to change it. So let's say I swap these two, I would have to put a negative sign here. And if I multiplied this by 2, I would have to put a half here.
Yeah, but you said a 3x3 matrix is good because you don't have to.
No, you don't. You never have to do anything for any of them. You just do what's convenient, what's easiest.
What's the benefit of a 3x3 matrix? Like, why do you do this?
It's just an example. There's no benefit for 3 by 3. You can do this process with any size.
I could have sworn you said this like some benefit.
I think he said it was like smaller. Like a 3x3 is relatively small compared to like a 4x4 or a 5x5.
And then send you the power.
Yeah, I'm illustrating with a 3 by 3, but you can do it with any size. And the bigger the size, the more useful the method becomes.
Convert it into reduced
Right?
echelon form.
Because in general, if you have like a 5 by 5, you have to break down to 4 by 4s, then 3 by 3s, and 2 by 2s. With a 3 by 3, the next step is a 2 by 2, which is easy. So you can just do it straight, you don't have to. But with like a 5 by 5, now it's like, oh my god, instead of doing all these calculations, let me just create a bunch of zeros so I can reduce the number of calculations.
If you get a column of all zeros, is it no solution like with a row of all zeros?
The thing is, you'll never be able to do that using a type 3, unless